Something new just streaked through our cosmic neighborhood. It came from the dark, cold space between the stars. It is a traveler with no home here. It crossed an unimaginable gulf to briefly visit our sun. On July 1st, 2025, humanity's watchful eyes caught a glimpse of this wanderer. We gave it a name, 3I Atlas. What is this mysterious visitor? Why did it journey all this way? And what secrets from its distant birthplace did it carry across the interstellar sea? The universe sends us messages, but not in bottles. It sends them in the form of rocks and ice, hurtling through the cosmos. This is one of those messages. The universe is vast. It is filled with countless stars, their own families of planets, asteroids, comets. For most of human history, we could only study the members of our own solar system. We were limited to our local family. But now, we are beginning to see evidence of visitors from other star systems. These interstellar objects are rare finds. So let's get right to the point. What is 3I Atlas? The simplest answer is this. 3I Atlas is an interstellar comet. It is a ball of ice, rock, dust that did not form around our sun. It came from another star system, far, far away. It passed through our solar system, and our telescopes were able to watch it. It is a genuine visitor from beyond. It is not an alien spaceship or a sign of doom. It is a natural object, a piece of another solar system that happened to wander into ours. Its name tells part of its story. The 3I means it is the third interstellar object ever confirmed by humans. The Atlas tells us which survey discovered it. A comet is often called a dirty snowball, or an icy dirt ball. It has a solid core called a nucleus. This nucleus is a mixture of frozen gases, like water, carbon dioxide, carbon monoxide, all mixed with dust and rock. When a comet gets close to a star, the heat begins to warm its surface. The frozen gases turn directly into gas in a process called sublimation, erupting and carrying dust with it, creating a coma and the comet's famous tails. 3I Atlas showed all these classic signs: a growing coma, a faint tail that pointed away from the sun. This activity is what separates a comet from a simple asteroid. The fact that it was active was a huge clue for scientists. It meant we could study the gases it was releasing, a direct sample of the stuff it is made of, preserved in a deep freeze for eons. This object is a precious sample not just from outside Earth, but from outside our entire solar system. How do you find a small, dark object moving against a backdrop of millions of stars? You need a dedicated watchman, or in this case, a team of robotic watchmen. On the night of July 1st, 2025, one of these robotic systems made the discovery. The system is called ATLAS, Asteroid Terrestrial Impact Last Alert System. Its job is to scan the entire night sky over and over, looking for anything that moves. Its primary goal is to find asteroids that might pose a threat to Earth, but sometimes it finds other amazing things. That night, the Atlas telescope in Chile spotted a faint, fuzzy dot moving slowly across the star field. At first, it looked like another new comet. The computers flagged it for follow-up. Astronomers around the world were alerted. They pointed their telescopes to get a better look. More observations came in, and they started to plot its orbit. Then things got really exciting. The path was not a closed loop, like an ellipse. The path was a hyperbola, an open-ended curve. This was the smoking gun. A hyperbolic orbit means the object is moving too fast to be captured by the sun. It came in from one direction, and it will leave in another, never to return. Think of it like a marble rolling past a bowling ball. If the marble is slow, it can be captured and circle. If the marble is fast, it curves and keeps going. 3I Atlas was moving that fast. Its high speed and open-ended trajectory were definitive proof. This object was not from around here. It was a true interstellar traveler. Once confirmed, it became a top priority. A worldwide campaign began. The path of 3I Atlas tells a story of cosmic loneliness and gravitational encounters. It did not travel in a circle or an oval around our sun. Most objects in our solar system do that. Planets, asteroids, most comets. They travel on closed orbits, like runners on a track. They might take years or thousands of years, but they always come back. 3I Atlas is different. Its path is a hyperbolic trajectory, an open path, not gravitationally bound to our sun. It is a one-time visitor, just passing through. Imagine its journey. Long ago, in a star system we can only guess at, this small, icy body formed and orbited its parent star. Then something happened. Perhaps a close pass with a giant planet like our Jupiter gave it a gravitational kick. That kick could have flung it out of its home system, ejecting it into the vast, empty space between the stars. For millions, even billions of years, it drifted in near-total darkness at temperatures just above absolute zero. Its original ices remained perfectly frozen, like a message in a cosmic freezer. By sheer chance, its long path brought it into our solar system's sphere of influence. The sun's gravity pulled. Its path bent. It accelerated inward. That bending allowed us to see it. It looped around the sun, not too close, but close enough to become active, and then began its journey back out. The sun could not hold it. This hyperbolic orbit is the key evidence that it's interstellar. The mathematics are clear. An object with that much energy and speed could not have originated here. It came from the outside, already carrying extra velocity. By tracing its trajectory backward, astronomers can estimate the direction it came from, a clue to its galactic region, though finding its exact parent star is nearly impossible. The galaxy is busy, and its path has likely been altered many times. What is this cosmic snowball made of? This is one of the most exciting questions because the answer tells us about the chemistry of another solar system. Comets are time capsules. The ices they contain are pristine samples of the material from which they formed. By looking at the gases in the coma of 3I Atlas, astronomers could read its chemical recipe. They used spectroscopy, breaking the light into colors. Different molecules emit at specific wavelengths, like chemical fingerprints. Analysis from telescopes like the James Webb Space Telescope revealed something fascinating. The comet was very rich in frozen carbon dioxide, CO2. It also had water ice, H2O, and a smaller amount of carbon monoxide, CO. The high amount of CO2 was a major finding. In our solar system, comets vary widely, but a comet this rich in CO2 is unusual, and it points to where 3I Atlas was born. It likely formed in a very, very cold place. Close to a star, even water ice cannot last. Farther out, you cross the snow line, where water freezes. Even farther, in the frigid outer reaches, CO2 can freeze solid. The CO2 frost line. So 3I Atlas, being CO2-rich, suggests it formed well beyond that line, in the cold, distant suburbs of its system. This is a profound clue. It tells us other systems have cold outer regions like ours, but their specific ratios, lots of CO2, less water, might differ from our Kuiper belt. Maybe the star was different, or the disk's temperature profile changed the chemistry. Every chemical detail from this visitor teaches us about planetary diversity across the galaxy. It's pretty remarkable. This discovery was not the work of one person or one telescope. It was a massive team effort. A beautiful example of global scientific collaboration. It all started with the ground-based Atlas survey, which made the initial detection. But to really understand 3I/Atlas, we had to call in the heavy hitters. We had to point our biggest and most powerful eyes in the sky at this fleeting target. Each telescope brought a unique capability to the table, and together they painted a complete picture. The Hubble Space Telescope, high above the atmosphere, was tasked with getting the sharpest possible images, distinguishing the tiny bright nucleus from its vast, diffuse coma, and refining the orbit with precise astrometry. Then came the James Webb Space Telescope, the master of infrared. The light of heat, perfect for studying cold gases. Its spectrographs identified CO2, water, and carbon monoxide and measured their abundances. Meanwhile, on the ground, the Vera C. Rubin Observatory in Chile, even during commissioning, tracked 3I/Atlas night after night, building a detailed movie of its motion and brightness changes. This stream of data helped model the comet's activity, how sublimation brightened and faded it. Together, these great observatories, Hubble, Webb, Rubin, and many others, acted like a team of cosmic detectives, piecing together the clues left behind by 3I/Atlas. So what did this comet actually look like? To the naked eye, it was completely invisible, far too small and faint. Through powerful telescopes, its cometary nature emerged. The solid core, the nucleus, was estimated to be very small, likely less than 1 kilometer in diameter, smaller than a medium-sized mountain on Earth. This tiny nucleus is the source of all the action, the icy heart of the comet. But we could not see it directly. It was shrouded by the bright cloud of its own making, the coma. As 3I/Atlas got closer to the Sun, solar radiation heated its surface. The frozen carbon dioxide, more volatile than water ice, began to sublimate vigorously, turning from solid straight to gas. Outgassing created a huge glowing atmosphere around the tiny nucleus. At its peak, the coma might have swelled to tens of thousands of kilometers, larger than Earth, yet incredibly thin, a near vacuum of gas and fine dust reflecting sunlight. And of course tails, dust pushed by sunlight and an ion tail, gas ionized by solar UV and blown by the solar wind. The tail of 3I/Atlas was faint but detectable, pointing directly away from the Sun. The presence of the tail was a clear sign of activity. Unlike asteroids, passive rocks, comets are dynamic mini-worlds that change day to day as fresh pockets of ice erupt. By watching the brightness and the coma and tail shapes, astronomers learned about its rotation, the distribution of ices, and how it responded to the solar environment. 3I/Atlas performed for us, a show that revealed its fundamental properties. Whenever we hear about a new object from space, a common question arises: is it coming for us? Is it a danger to Earth? In the case of 3I/Atlas, the answer is a clear and resounding no. This interstellar comet poses absolutely no threat to our planet. Astronomers calculated its trajectory with high precision shortly after discovery. Its path was well understood, never destined to come anywhere near Earth. It did not get any closer than about 1.8 astronomical units, roughly 270 million kilometers, almost twice the Earth-Sun distance. It's a passerby, not an impactor. The other side of the street, and then some. Staying farther from the Sun meant it remained intact, allowing a longer, more stable observing campaign without the chaos of a violent breakup. Hollywood loves drama, but the reality of 3I/Atlas is serene. It is a messenger, not a menace. Its purpose isn't destruction, but to deliver information. A physical sample from a distant star system, studied with our best instruments. It is a gift from the cosmos, a rare opportunity to learn. Greet such visitors not with fear, but with curiosity and wonder. In the end, what is the big takeaway? Why should we care about a tiny icy rock that came and went? We should care because 3I/Atlas, Oumuamua, and Borisov represent a fundamental shift in our understanding of the galaxy. For centuries, we could only study our own solar system. Now, the universe is sending us samples from other systems. Each interstellar visitor is a new chapter in the galactic story, and we are just learning how to read them. These visitors confirm a long-held theory. Solar systems are not closed, isolated islands. They are messy. They throw things out. Planet formation is chaotic. Billions of small bodies, comets, asteroids, are ejected into interstellar space. The galaxy is filled with homeless wanderers. By studying the ones that pass by, we can build a census of what other systems are made of. 3I/Atlas, with its carbon dioxide-rich composition, tells us some systems are different from ours. This matters for the biggest questions: origins of planets, origins of life. Comets are thought to have delivered water and organic molecules to the early Earth. If interstellar comets like 3I/Atlas also carry these ingredients, it suggests the building blocks of life could be common throughout the galaxy. It raises the possibility that the stuff needed for life is not unique to our solar system, perhaps delivered from star to star by icy messengers. A small traveler came from a far star and passed through our cosmic backyard. It left no trace except in the data recorded by our telescopes. But those clues are precious. They tell us a story of a cold, distant birthplace and teach us that the universe is more varied and more connected than we ever knew. And we now know this was not the last visitor. With new telescopes, like the Rubin Observatory coming online, we expect to find many more interstellar objects in the coming years. Each one will be a new piece of the puzzle. Each one will bring us a little closer to understanding our place in the great grand cosmos.